All right, so section 11.4 is geometry in 3 dimensions. We started this last time, and we talked about these shapes right before we hit a big, giant box. And let me flip back to what we were talking about. What we were talking about was the 5 regular solid polyhedra called Platonic solids. There's only 5 of them. And these are the 5 different images, and we'll see them show up over here on the right-hand side of this box. So I know I mentioned the first one last time, the tetrahedron. A tetrahedron is like a triangular, 3-dimensional shape where all the sides are triangles. They're all equilateral triangles. There are 4 equilateral triangles, and we mentioned last time before we left that I used this point at the top here as an example point, that at that point there's actually 3 faces, namely 3 triangles in this case, all meeting up at that same point. The next one, which you're very familiar with, is a cube. We use cubes all the time. My first grader is learning how to draw a cube, right? So cubes are introduced really young. There are 6 faces, and the faces are all squares. And if you take, again, an individual vertex, there are 3 squares that meet at that point. The next one is an octahedron. An octahedron has 8 faces, and the faces, again, are equilateral triangles. It kind of looks like you took 2 tetrahedrons and stuck them together, but it's also not quite that, right? This shape that forms in the middle of sticking them all together is not a triangle base, so it isn't just 2 tetrahedrons stuck together. It almost feels like that, but it isn't. In particular, if you take any vertice, we'll take the top one, you actually notice that there are 4 triangles meeting up there now, not 3. That's also different. The dodecahedron, dodeca, that phrase, kind of like that one that you had asked earlier, Hannah, where you saw the dodecagon, means 12. So we're getting a 12-faced polyhedron on this one. So it's actually 12 equilateral, or regular pentagons. So drawing some of these is very challenging. I'm not going to ask you to draw a dodecahedron, promise you, okay? But you can see that shape over there. If I take one of the corners, I'll take this one. You can see that there are 3 pentagons that are all meeting at that corner. This almost starts to feel a little bit like a soccer ball would feel or something. It's not, because on a soccer ball you don't just have pentagons, you also have hexagons, but it's similar feeling. And the last one is an icosahedron. An icosahedron has 20 faces, and they're all triangles. So you have 20 triangles, and at each vertex, we'll use the bottom one, you can see that there are 5 faces that are meeting at that same vertex. You may or may not be able to see that there are 5, but there are 5. Okay. Now, anytime you're able to take a polyhedron like this, and it doesn't even have to be a regular one, if you were able to sort of cut it in a certain way and lay it flat, that image that you get by laying it flat is called a net. Okay, so it's just the flattening out of the faces of a polyhedron. Now, these specifically are referenced to the regular polyhedra, the ones from the previous slide. And so what you can see is you can see what it looks like when we flatten these puppies out. So the cube isn't too difficult to imagine that if you fold it along the dotted lines, and actually along this line as well, folded, and this one and this one. So you got all these folds here. That was terrible. There. And you pieced it back together, you would create the cube. Okay, every now and then one of my 6th graders likes to cut things apart and turn things into 3-dimensional. I don't know if you guys ever did that. I know I did too, but it specifically happens in my house every now and then. So a cube is one of the ones that we sort of are familiar with sort of doing this with. The tetrahedron is probably the easiest to imagine doing this with, right? If you folded it along those 3 dotted lines, it would fold up to the top and it would actually make a pyramid. Right, we talked about pyramids before. We'd have them all touching at the top, the apex. The octahedron would fold all together as well. We have the dodecahedron. There's all those pentagons all separated out flat. They look like flowers. And then the icosahedron, which looks somewhat like an Argyle sweater, or something like that. So these are different nets for those specific shapes. I think this is one of our last things that we're going to look at in this section, this particular part of the section about these shapes, the polyhedron shapes, Euler's formula. Euler's formula, notice it says, and it's true, that this works for any polyhedron, not just the regular ones, but for any of them. If you take the vertices plus the faces and subtract off the number of edges, you always end up with the magic number 2. I'd probably put that on your card. It's a pretty important formula. It's very easy to ask questions about that particular formula. So we're going to take just a couple of them. I don't care which one we do, so I'm going to throw it out there and let y'all pick. We had 5. We're going to do it. I know it says we can do this in general for any polyhedron, but we've got 5 of them over here that we can use. So let's just pick one of them and check it out so that you can see that it works. So somebody pick one for me. Which one? The cube. Okay, so we'll do the cube. Now, some of these are actually inside of the slide here itself. I have 6 faces, and we can actually count some of the other images really quick. So I have 6 faces, so that's my faces. I need to count my vertices, so I've already got one of them in green. So here's 2, 3, 4, 5, 6, 7, and 8. So my vertices is 8. And then we're going to count edges. So I have 4 vertical edges, 1, 2, 3, and 4. I have 4 edges around the top, 1, 2, 3, and 4, and 4 edges around the bottom. So how many edges do I have total? 12. So these are my 3 numbers that I'm going to be using. I have 6 faces, 8 vertices, and 12 edges. Now yours is on your same piece of paper. I need to flip across my slide. So if I'm doing my cube, and I had, what were my numbers again? Let's see, my faces was 6, my edges was 12, and my vertices was 8. All right. And what this says that I should be able to do is vertices plus faces minus edges. And that should equal 2. So my vertices was 12. My faces is 6. And my edges is, I'm sorry. Vertices was 8. I got off my screen. Too much zooming in and out. This vertices is 8. Faces is 6 and edges is 12. So what is 8 plus 6? 14. And what's 14 minus 12? 2. So it works. Let's try one more. What's another one you want to do? We did the cube. What else? Dodecahedron. Okay, so I'm going to flip back over and we're going to try and identify all the pieces again. So I have one of them already written, right? The faces. So faces is 12. All right, so let's see if we can count something. It's got a lot of counting because Elizabeth wanted us to do the fun shape. All right, so let's count our vertices. We have 5 here in the middle. I have 1, 2, that's 5 more here, so that, or 4 more here, so that's 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There should be 20. Where did I miss it? Maybe I just counted wrong. There should be 20 vertices. I probably didn't mark something right, but there's 20. So I've got vertices is 20. The edges are really hard to count. If you count up all the edges, you will end up with having 30 edges. I'm not sure if I can count them from our picture here at all, but we're going to try. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, definitely recounted something. There's 30. There's 30. They're messed up. There's 30. I should have like a shape and you guys can all touch and feel and shape it, but it's 30. So we have 12 faces, 20 edges is 30, and vertices is 20. And so I'm supposed to take my vertices plus my faces minus my edges. So the vertices is 20, faces 12, minus my edges, which is 30. Do I get 2? I do. And of course, not all shapes even need to be regular to do this with, but they definitely do work for our regular shapes. Okay, we have a couple more three-dimensional shapes we're going to talk about, and then this lesson will finish up. Oh, I did it for 2 of them over there. It says for 3. Are you guys good with 2 being enough? All right, cool. Did it on the wrong slide, but it's there. All right, 2 more shapes, cylinders and cones. A cylinder is not going to have all the same straight edges that my polyhedron did. So specifically, a cylinder is a simple closed surface that is not a polyhedron. It has bases that are not polygons, and it has one smooth lateral surface with no edges. Now, imagine a toilet paper roll. Seems fitting, we just finished 2020, right? And if you were to unravel one layer that goes all the way around, just one layer, that's that lateral edge it's talking about. And you could lay it flat and it would look like a rectangle, right? That's the lateral face. Now, you don't have to have a circle top and a circle bottom to be a cylinder. We have lots of examples of cylinders that we purchase all the time, or near cylinders, right? This is a near cylinder, my water bottle, yeah? Your cans, soda cans, canned products like green beans or something like that, those would be cylinders. Also our rolls of things like toilet paper, at least ignoring the fact that their thickness is filled in. But in reality, that's true for all these objects. Our shapes actually are not supposed to be filled in to be these images, they're hollow. So that's a cylinder. A little bit more about cylinders, a couple different types. A cylinder that you know and love, right? The toilet paper roll, paper towel roll, the can, is a right circular cylinder. Has a circle on the top and the bottom, and it's sort of straight up and down. It's not leaning. So it's called a right cylinder because it's straight up and down. Forms that right angle at the, to the base of the can and the top of the can. And it's circular because the top and the bottom are circular. If you have the leaning, it's called oblique, just like we did before with our other shapes, our pyramids and our prisms. You turn it onto a slant, we have an oblique shape instead of a right shape. We also don't have to have circles on top and bottom. So this first image right here where it has this sort of, pond-like shape or something on the top, right? I don't know what you want to call it, but whatever it is, it's the same image on the top and the bottom. So it is creating a cylinder, but it's not circular. It is a right cylinder though, isn't it? So this is a right cylinder. You can imagine if we were drawing it from the center, something like this and down, it's straight up and down, but it's non-circular. So you can have oblique, you can have right, you can have circular, you can have non-circular, and they all can still be cylinders. The other one that we have here at the end is a cone. A cone is determined by a simple closed curve, which creates the base, but it's not a polygon. It's in a plane, and then you take a point not in the plane, we call it the vertex of the cone, and you connect them. Cylinders feel like the circular option that corresponds with prisms, right? Base on top, base on bottom, and they're connected on the sides. Cones feel like the connection with pyramids. We have a point on top, and we have one base on bottom that it connects down to the sides. The cone also has a smooth lateral surface with no edges. So imagine, the best image is not a waffle cone, but imagine a sugar cone. Do you guys know what sugar cones are? Those people at Brahms sometimes don't know what I'm saying if I say sugar cone. The sugar cones are the little ones that look like waffle cones. They're not waffle cones, and they're much, much older. Like, they've existed a lot longer than the waffle cone has. But they're a far better picture of what a cone is by the description we're doing here, because it is more of a smooth outer surface, right, as opposed to having the flopped over piece that the waffle cone creates. If you don't eat ice cream, I'm really sorry that I don't have a reference point right now that's connecting with you. But I hope you eat ice cream because it's really good. So our cone, it's a sugar cone, has the same sort of image that we have here. The line segment from the vertex to the base, right, that goes from the top down to the center of the cone is called the altitude. And here's an image for you. You can see that little red sort of corner down here at the bottom. From the vertex down, right there to the center, that's my altitude. The lateral surface is the exterior shape, and my base is this shaded in blue piece at the bottom. This would be a right circular cone. This would be an oblique circular cone. Now, the reality is it doesn't have to be a circle either, right? There was nothing in the description here that said that I have a base that's a circle. So if you could imagine taking this sort of pond-like shape and doing the vertex down at the bottom or the top and connecting them, you could still have a cone. It would just be a non-circular cone. And maybe it would be right, or maybe it would be oblique, depending on the shape of the slant or something like that. But you could have it still be non-circular. I think I got just about everything. Yeah, so we had a right circular cone and our oblique circular cone, and we're finished. All right, cool. All right, so group work. We're going to take a look at here in class today. We have a few minutes to get started, 8 minutes or so. And then the homework. Both of these will be due next time when you come to class. So come with questions. We'll do just like we did today. Come with questions from 11-4. We'll start with those and then upload them afterwards, unless you're already ready and you don't have any questions and you can upload them sooner.